Good morning, everyone. Today we're going to be covering a really deep dive into waves and how they interact. Start with a good introduction as to what a wave is. You can have two types of waves. You can have a transverse wave and you can have a longitudinal wave. Okay, transverse waves. The classic transverse wave, it looks like the oscillation we all think of. Okay, the longitudinal wave is a bit more difficult to visualize. I'll explain what those lines mean in just a moment, okay? So let's first start with the transverse wave. The inherent in the quality of a wave is it displays periodicity. Means it has one defined unit or section that repeats, and it repeats every time a certain period of time passes, okay? The example here in the transverse wave would be, or let's say, peak to peak. Everything that occurs between one peak and the second peak happens between the second peak and the third peak, okay? So it repeats perfectly over and over and over again, all right? Everything between this downward midpoint and that downward midpoint repeats perfectly. Everything between one trough and the next trough continues to repeat perfectly, okay? The time it takes for the wave to undergo one such unit, one such transformation is called, you guessed it, the period, okay? And the period is in units of seconds, because it says how many seconds does it take for the wave to undergo one unit of propagation, okay? Period is related to a quantity known as frequency, and is related to said quantity by 1 over period equals frequency, and vice versa. 1 over frequency equals period. Okay? The frequency is a unit that states how many units pass through or pass every second. How many units occur in a second. The units of frequency, as we can see by this relation, are units of 1 over seconds. The units of 1 over seconds are known as hertz. So let's continue to understand the qualities of this wave. All right. The wave constantly oscillates above and below a certain rest line, a rest position. So this total vertical displacement of the wave we're going to call h. So 1/2 of h is equal to our amplitude, which would be this metric right here. That would be our big A amplitude. So what exactly does the amplitude represent? It represents the maximum displacement that our wave occurs from the rest position, okay? So an amplitude is experienced both in the positive and negative direction, but your amplitude is always a positive quantity, okay? Since the amplitude in the negative direction is always equal to the amplitude in the positive direction, there is no reason to have two amplitudes, or a positive and a negative. Amplitude is proportional to the energy of a wave. Higher amplitude means higher energy. Frequency is also proportional to the energy of a wave. So these are the components of a wave we're going to want to know. We're going to want to know what amplitude is, we're going to want to know what frequency is, we're going to want to know what period is, and we're going to want to know what wavelength is. Lambda or wavelength is the physical numeric distance between 2 points in a period, okay? So your wavelength could be between any 2 points, such that those 2 points are the start and end point of a period, okay? So your wavelength could be measured here, your wavelength could be measured there, it could be measured there. Or at any 2 points that measure the start and end of a period, okay? Your wavelength is related to your frequency by an equation given to you on your equation sheet, which is lambda equals v over f. Lambda equals velocity over frequency. The v represents the velocity of your wave, okay? In the case of electromagnetic waves, which include light and radio waves, etc., v equals c. c being a constant given to you on the front page of your reference table, which is the speed of light. If you are not dealing with an electromagnetic wave, your velocity would be determined using other means. We're going to cover some of the equations with strings later in the video. So these are your 5 characteristics of the wave that you need to be able to familiarize yourself with. Amplitude, frequency, period, lambda. I call it lambda, I don't usually call it wavelength, just get used to that. And velocity, okay? Frequency, lambda, and velocity are interrelated. Frequency and period are interrelated. Amplitude kind of exists in a vacuum. Okay, let's move on to the longitudinal wave, okay? Now the first thing I want you to take notice of when you look at the longitudinal wave is these lines are not randomly drawn. There are periods of high density, periods of low density, periods of high density, periods of low density, periods of high density. So I'm going to denote density, high densities with D. Okay? That is the nature of the wave. It is a wave that travels through air or any fluid, as a matter of fact. And the lines here are to represent wave fronts in the fluid, okay? So in the dense section, you have a lot of molecules in the fluid being compressed very close together, and in the depressed wave fronts, you have molecules in the fluid being sparsely apart. And the nature of the wave is that in a given position, let's call this position X, the density of the molecules in the fluid will constantly oscillate between compressed and incompressed and compressed and incompressed, such that it would give the impression that the wave is moving further to the right. There should be a GIF on the screen right now that allows you to better visualize the longitudinal wave with the telltale example of sound. Sound is the best longitudinal wave example that can be demonstrated. And you'll notice that the molecules are not moving in a, let's call it, significant displacement. The molecules are oscillating back and forth, though remaining within the area closest to their resting position. They are not all moving together. The molecules do not have a velocity. They are in a harmonic oscillation. Okay. So moving on from there, we have some equations that we use to define and help us understand waves. Those would also be present on your reference table in the bottom corner of the 3rd page, okay, just above your geometry and trigonometry table. Okay, those are x sub t. Well, it's not written right, okay? It's better written as y sub t, y as a function of t, equals a cosine omega t, which equals a cosine 2 pi frequency t. Now, these two equations are the same because omega equals 2 pi f. Like it's just this one substitution made between these two equations. Otherwise, they are exactly the same thing. And you can understand why these two are the same if you take a look at the harmonic oscillator unit in AP Physics 1, the equations of which I believe are still present on page 4 of your reference table. Okay, so moving on from there, we have a different equation underneath that on your reference table, that y as a function of x is equal to a cosine of 2 pi x over lambda. So first and foremost, what do we notice? We notice that there's a 2 pi present in all these equations. That means that your calculator must be put into radians mode when you try to answer questions dealing with these equations, okay? So if you have no clue what I'm talking about, I'm going to show you right now. Okay, so this is my TI-84 calculator. Usually I'm going to plug in cosine of 45 degrees. Well, let me put in cosine of 90 degrees, and that's going to give me something that isn't cosine of 90. Cosine of 90 is supposed to be 1. Why is that? Because if I press second, well, not second, excuse me, if I press mode, I press that, and I scroll through the settings in my calculator, I'll be able to see there is 2 options I can switch from here. There's radian mode and there's degree mode. Right now my calculator is in radian mode. When you are dealing with these equations, you need to have your calculator in radian mode, okay? So if I press second and mode is quit, if I go back to my screen, this is cosine of 90 radians that I just put into my calculator. Okay, it's going to be much easier to understand these equations in the context of this graph, okay? So all of our equations started out as cosine of something, okay? But that is not a set in stone rule, okay? Here you can see me drawn out a wave. However, that wave starts at 0, okay? It doesn't start up here at 1. Therefore, this wave is demonstrating a sine curve, okay? So if we notice that our wave is in the shape of a sine curve, we need to switch out our cosines for sines, okay? So it's important to be attentive of that. Anyway, let's start to analyze these equations. It's best separated into 2 parts. You have your sine function here, and you have A. What's A? It's your amplitude. Okay, so your amplitude, as we discussed, is just the maximum displacement that your wave can have. Okay, so your position on the y-axis of your wave can never exceed the amplitude in either direction. Okay, and sine or cosine in other cases can never exceed 1. The cosine and sine constantly oscillate between 1 and -1. Therefore, your position on the y-axis can never be more than A and never be more than -A. So up here, your position would be A. Down here, your position would be -A. Okay? And what's inside of the sine or cosine function is just a figure that determines how fast or how frequently you oscillate between A and -A. Okay? So I don't think you need an explanation of what's inside. You just need to know what to plug in. 2 pi, that's usually that's just a constant. Pi isn't changing. You have lambda. Your wavelength lambda shouldn't be changing, but it's something you're going to need to calculate usually, or it's going to be given to you. X is your input. It is the input that your function is dependent on. And frequency is also something that you may be given or you may need to calculate. Time would be, again, your input. Okay? Frequency lambda would be calculated using this equation, using one or the other. But let's discuss first the difference between these 2 equations. One is your height of the wave y as a function of time. So this wave propagates through time, meaning as time goes on, this wave will continue propagating in whichever direction it's going. It might be going to the left. And this function y gives you your vertical position as a function of the horizontal position x, okay? So it basically says if I'm at this point on my wave, what is my height? That's basically what this equation helps you do. Okay, let's move on from there to interference, okay? What is interference? Interference is when 2 or more waves overlap, okay? Waves do not collide, they don't hit each other, they combine, okay? So if I have a wave that looks like this, and that wave is going to combine with a wave that looks like this, they combine linearly, okay? Meaning everything adds together. Let's try and look at a graph of the resulting wave. So if we look at these, this one on the bottom is just moved slightly to the left, reference to this guy on the top, okay? So let's consider it point by point. That's what you got to do when you add waves. At this point, one wave is positive, the other wave is positive, so both of the waves are going to add to an even bigger positive. Here, one of the waves is negative, one of the waves is 0, one of the waves is negative. So that's just going to be the original negative of the bottom wave. Here, both of them are negative, so it's going to make an even bigger negative. Here, both are negative. Again, it's going to make an even bigger negative. Here, one is positive, one is negative, so they're going to cancel out, okay? And it's going to get approximately 0. Here, they're both going to add again. So you can see that the trough of this wave, the lowest point, is going to appear about here, okay, which is approximately between the lowest point of this wave and the lowest point of this wave. Now, alternatively, you can have interference that is completely and utterly destructive, okay? Destructive interference looks like when one wave is drawn as such and one wave is exactly the opposite, okay? Such that all the lows add to the highs and all the highs add to the lows, and if that's the case, then they both completely cancel each other out and you get a flat line. In this case, the one drawn right here, the peaks on both waves are almost but not completely aligned. If they were completely aligned, you would have completely constructive interference, where there is no change in the wave, but all of the peaks and troughs are just amplified. Your amplitude only grows. Interference is a very important concept to consider when we talk about standing waves, okay? What is a standing wave? A standing wave occurs when you have a wave that is trapped in a finite space. A perfect example of that would be a string. So once we have a string, how do we confine it? How do we trap a wave to a finite space? Well, we nail both ends of the string to the wall. So both ends of the string are completely fixed. They can't move, okay? Perfect example of that would be like when you were little and you made your little homemade guitars out of a tissue box and some rubber bands. Those rubber bands were fixed at each end of the tissue box, and you created waves when you strummed the rubber bands, okay? So that would be a real-life example of this. If I were to create a little oscillation here, then that oscillation would continue to propagate until it hit the other end of the string, okay? So if it hit the other end of the string, that other end will reflect the wave back this way, okay? Except this time, if a wave reflects back, it's going to be inverted, be the same exact drawing, but in the opposite direction, moving this direction, whereas previously it was moving that direction. If I strum the string once, I'm not going to create a standing wave. I'm going to create a wave that oscillates from one end to the other and is reflected back and forth, etc. But if I strum it and I continue to wiggle it, meaning I continue to generate a wave on this end, it's going to reflect back and there will be a continuous back wave coming from the opposite end, okay? So in that case, when I'm continuously supplying a wave, the wave that I'm supplying and the wave that is being reflected back at me will interfere with each other, okay? So a standing wave is created when a wave is transmitted, reflects off a surface, and then proceeds to interfere with itself. Like I showed you here, interference can create a whole slew of waves, and it's a really big mess, okay? When we create standing waves, which is in the example I just showed you, standing waves will prefer to exist at certain wavelengths, okay, certain lambda. And those lambda can be identified by the equation 2L over lambda equals n. So let's understand where this equation comes from. First, we need to understand a little bit more about standing waves. Standing waves have characteristics known as nodes and antinodes. Okay? A node is a location on the finite space, the finite area, that never moves. Okay? In this case, we have two nodes. One is this end that's hammered down, the other is this end. We have two nodes. Okay? The preference of standing waves is they strongly prefer to exist when the number of nodes is constant. Okay? So let's return to this example I had drawn here. Waves are moving. This wave has a net velocity to the right direction, okay? Meaning this point that is currently 0 now, after the wave moves a little bit, the wave will look like this. So the point that was 0 here has now become this point, and that previous point is no longer 0, okay? Nodes are points in which the magnitude of the wave is always 0. So the magnitude of the wave will always be 0 at the endpoints in this case, but if I were to draw a wave like this, then I would have a node right here. Because the characteristic of a standing wave is that it doesn't move. It only oscillates top to bottom. Okay? I should have a GIF up here of what a standing wave looks like. Okay, and remember that a standing wave is formed through the interference of two waves moving in opposite directions. Usually the two waves are one wave reflecting off of a wall. Okay? So, mathematically, how do we find the wavelengths that create a node, or 0 nodes, okay? If we are given the length of our space, and let's say we want to have 0 new nodes, okay? If we want to have 0 new nodes, then our wave can't cross the center axis. So we would have a wave that looks like that, okay? And if we extended the wire, it would continue on like this, okay? So let me draw that out for us to better visualize the representation of the wave, all right? So what if this one point to its opposite point in the period, this whole wavelength is our lambda, okay? So in this case, the longest wavelength we can have, the wavelength that produces 0 nodes, is 2L, a lambda that is twice the length of our little wire here, okay? So that is what this equation is telling us. 2 times the length of the wire, or the length of the space, divided by our lambda must equal an integer. That is what this n means. It could mean any integer, 1, 2, 3, etc. When our integer is 1, that is what we call the first harmonic. And the first harmonic is what we call the fundamental wavelength, the fundamental lambda. Okay? You just need to memorize that that's what it's called. The second harmonic, as you might have guessed, is what happens when we set n equal to 2. The second harmonic, if we calculate that out, is L over lambda. 2L over lambda equals 2. Therefore, lambda equals L, okay? If our lambda equals L, then our wave is going to look like this. So we have one node. And this is going to be our second harmonic. To what happens when waves are transmitted or reflected. Okay, now this occurs when we have a change in conduction media. Conduction media referring to the substance or space through which a wave propagates. Okay, so let's return to our string example. Okay, so on your reference table, you are given an equation that helps to determine the velocity of a wave as it travels along a string. Okay, that equation is given as velocity substring equals the radical of the tension force in the string divided by mass over L. So F sub T over M over L, okay? So mass divided by length might resemble the density formula, mass over volume. That's because this little section, mass over length, is what we call the linear mass density. Little fun fact right there. So this would be an example of where you don't know the velocity of the wave, and you're going to have to calculate it using one of the equations you're given. Okay? So let's say I have two strings here. Let's say for the first example that the dotted line exactly the same as the red line, except this one has a greater tensile force being applied to it. Okay? So what does that mean? It means that if these are the same string and this one has greater tensile force, the velocity of a wave in this string will be greater than in this string. Okay? So if I have a wave propagating through this string to the right, it's going to contact the meeting point, and part of the wave will be transmitted into the second string and part of the wave will be reflected back. Okay? So what does that look like? I've got a wave, it's coming in, it hits this point. Some of the wave continues on exactly the same frequency that it was going earlier. Some of the wave is going to be reflected back. Again, exactly the same frequency it was going earlier. So in any collision or transformation that occurs with a wave, frequency is always held constant. Frequency is always held constant. But we referenced here that frequency and amplitude are both proportional to the energy of a wave. Okay, so if I start with one wave and that wave splits into part of a wave that is transmitted and part of a wave that is reflected, due to conservation of energy, the two waves that are the product of after the collision must have less energy each than the single wave that produced the two of them. Okay? So what does that mean? If energy decreased for each wave individually after the collision, their amplitude must have decreased. Okay? Now, when we refer to transmission and reflection, if we have a wave that's progressing like this, the wave that is transmitted to the second wire will have absolutely no interruption in its phase. Okay, what do we mean by phase? We mean by the position of the wave in the x-axis relative to this guy, okay? So even though amplitude will be decreased, frequency will remain constant and it will connect seamlessly to the previous wave, okay? That is for the wave that is transmitted, okay? For the wave that is reflected, it's a little more complicated, okay? Let's first consider this particular scenario in which we have two wires in which the second wire, the speed of the wave would be higher should it be transmitted, okay? So in that particular case, when wave travels faster in the second medium than the wave that comes in, will be reflected back exactly as it came in, okay? So it's going to look like that, except before the collision is going this way, after the collision is going that way. In the case that it's going faster on the right, the reflected wave will be the exact same as the one coming in. In the event that is not the case, meaning velocity would be lower on the right, then the wave coming in would hit the border, and it would be reflected exactly as the inverse. Okay? Notice how These are perfectly in phase. These are exactly 180 degrees or pi radians out of phase. Moving on from there, we have the Doppler effect. Okay, scary name, not that hard to understand. What is the Doppler effect? It states that if I have, let's say, a wave that is a light, say it's green light being emitted from a laser beam, okay? I got a laser beam emitting green light, okay? And as an observer outside, I'm going to observe this photon, this wave of green light. Since the light is traveling in this direction, reference to a stationary measuring device, we know that the frequency is some amount, okay? However, if the measuring device is also moving in the same direction, then the measured frequency will be less because of the way in which we measure frequency. Frequency is measured by how many oscillations come through the sensor every unit time, okay? So if the sensor is also moving in this direction, then less oscillations are going to be able to move through the sensor because they're trying to catch the sensor, okay? So a lower frequency is to be expected when you measure as this in such a way, okay? Alternatively, the sensor could be moving in the opposite direction relative to the propagation of the wave, okay? In this way, the sensor is moving across the wave and is measuring a greater amount of oscillations than would have otherwise passed through if it should be remaining stationary. It's like when you're eating a sandwich. If I'm eating a sandwich like this, okay, I'm gonna eat more sandwich if I'm also moving my head towards it, okay? And if I'm eating a sandwich like this, I'm gonna eat less sandwich if I'm moving my head away from it as I'm pulling it in. Makes sense. That's the Doppler effect, okay? Pretty simple. Next up, we covered that you can have electromagnetic waves. The unique characteristic of electromagnetic waves being that they do not need a medium through which to propagate. EM waves can propagate through a vacuum. That's how light from the sun can come to Earth. Okay? Now, the properties of EM waves in purely these aspects will be exactly the way I've described them earlier. Again, you have the unique case where your velocity is equal to the speed of light. We covered when that is not true in the previous unit. But for the AP Physics 2 exam, for some reason, they say that you need to memorize the general order of the electromagnetic spectrum. I should be putting that right here, okay? So you don't need to know exactly the frequencies and wavelengths at which certain EM waves are, but you should know the general order, starting all the way at the lowest frequencies here on radio waves, and then going all the way up to microwaves, the visible light spectrum, not infrared, ultraviolet, coming up to gamma rays all the way on the right. Polarization. If we look at a wave, specifically a electromagnetic wave, we'll notice that the wave propagates up and down in 2 dimensions, okay? So if instead of the laser pointer emitting the wave, I was observing the wave from the perspective of the laser pointer, I would see the wave like that. It's just a flat line, okay? The wave does not propagate in 3 dimensions. At least not that we are considering it to. A polarizer is a device through which a wave can pass. And that polarizer can be angled, okay? So the polarizer is going to have a little slit in it through which my electromagnetic wave can pass. And if my electromagnetic wave is perfectly aligned to the polarizer, then all of my wave is going to be able to pass through, okay? But if there is a mismatch, then some of my wave is going to pass through and some of it won't. And ultimately, that's going to result in a decrease in the intensity of the wave, okay? This is not an equation you have on your equation sheet, but it's a useful equation to know if you want to relate intensity. that the intensity after a polarizer is equal to the intensity of a wave before the polarizer times the cosine squared of the angle theta between the wave and the polarizer. Okay? Such that if I have a wave that is exactly perpendicular to my polarizer, cosine squared will always be 0. Or if I have a polarizer 1 and a polarizer 2 immediately after it that are perpendicular to each other, then whatever passes through one isn't going to be able to pass through the other. So in that case, my intensity will also be reduced to 0. But in any case between, your intensity will just be reduced slightly, Okay. Let's go on from there to what is arguably the most famous part of this class that we cover, which is the double slit experiment and the diffraction grating. Okay? So first and foremost, you have the single slit experiment, where I have a wall with a single slit in it, I have a wave, light wave coming in, and I have a wall on the back. Okay, so that light wave comes in, and once it passes through this little slit, single slit right now, it's going to diffract and interfere with itself to produce a diffraction grating across the back wall. Okay, what is a diffraction grating? For a single slit diffraction grating, it consists of a huge bright fringe of light in the, that is a horrible drawing, consists of a huge bright fringe of light in the center with several much smaller fringes as you go further out. Okay? That's your single slit diffraction grating. Now, the equations that you use to define this diffraction grating are your delta D equals m lambda. So I prefer to rewrite this as delta x equals m lambda. That just makes it easier for me to understand. The delta x in this case would be representing the distances between your fringes. That's your delta x. So delta x being a constant multiple times your lambda is signifying that if you want a larger delta x, you would be going to a further away fringe, okay? So if I call the center fringe 0, then my displacement is 0. But if I want the first fringe, m is going to be 1. If I want the second fringe, m is going to be 2, and so on and so forth, okay? The next equation that we are given to analyze the diffraction pattern is that our delta D, which again I prefer to write as delta x, is equal to a sine theta, where a is the width of your slit. A is the width of your slit, okay? And sine theta is going to be this angle theta that you make if I draw a perfectly horizontal line and a straight line from the slit to the fringe that I would like to analyze, okay? So this angle theta is the angle theta between those two lines, okay? Such that if I want to analyze the big fringe, my angle theta is going to be 0, and my delta x is going to be 0, which agrees perfectly, because there is no change in displacement if I'm calculating the center fringe. Okay, and these equations combine on your reference table with a little bit of trigonometric substitution to give you the equation A times y over L equals m lambda, okay? Such that A is again your width here, L is this length, L being the length between your diffraction grating and your back wall. That's your length L. Y would be the delta x that I would have been referring to previously. And of course, m lambda has not changed, okay? So given that y is our representation of delta x, if I want to analyze, let's say, the second fringe, I'd say m equals 2 times lambda, which would be known, is equal to my width, which would be known, times my y, which is the distance that I'm trying to figure out here, divided by the length between my diffraction grating and my wall. Okay, and in this case, I'd be able to solve for y given a, l, and lambda. Okay, so from there, we have a second type of interference pattern, and that is the double slit interference pattern, which abides by the literal exact same equations, but the concept is slightly different. Okay, so I'm not going to explain the equations the second time. This time I have a separator with two slits in it. Ah, so now I have a wave propagating towards the two slits. The wave passes through here and it passes through here, and that creates two wave fronts that interfere with themselves. Okay, so we can see the interference of the waves in real time. Okay, so on the back wall, consequently, the shape, not the shape, the distribution of the fringes is the only difference. So in this case, you would have a central bright fringe as you do in that one, but the fringes would be a lot more uniform and they would decrease in intensity a lot slower. Okay? So that is the difference there. And the exact same equations apply, as you can see on your reference table, where in this case, instead of identifying the width of our diffraction grating here, we are identifying the distance between our two slits here, okay? So the only difference is we replace A with D, such that our equation becomes d y over L equals m lambda. And it's the exact same process, exact same equation, okay? From there, we need to take a look at thin film approximations. So the gist of a thin film approximation, it actually combines a lot of this unit into one type of problem, okay? So in a thin film, I have one medium out here, let's call this N1, let's call this air, and that medium is in contact with a medium down here, let's call this N2, a very thin film of medium N2, and then a medium N3 that extends off the page and we don't care about it, okay? So this is the setup for our problem. Light from medium N1 is going to be incident on this boundary, okay? Some of that light is going to be reflected, and some of that light is going to continue moving downward. It's going to be refracted. And now, on the boundary between N2 and N3, some of that light is going to be reflected, and some of that light is going to be further refracted. Okay? So, these, we have now created two waves that extend out of the medium, and since these are two waves traveling in the same direction, these are two waves that are going to interfere with each other. Thus, thin film interference. Okay? So, let's start with our conditions for constructive interference. Constructive interference. That is when our troughs perfectly line up and our peaks perfectly line up. That means that relative to our initial wave, our second wave, the displacement, we can say, must be some constant multiple of lambda, okay? If I were to draw that out, I can shift the wave a total of one wavelength to the left, and it will continue with the same peaks and troughs. One wavelength to the right, excuse me. So it needs to be a constant multiple of lambda displaced either to the right or to the left, where m can be 0, okay? That is the condition for all of the peaks, troughs to line up, and we get constructive interference. Now for destructive interference, if we want perfectly destructive interference, we need to have a displacement between the two waves. That is m plus 0.5 times lambda, okay? So if I have a wave and I want to create perfectly destructive interference, I want to displace it exactly half a lambda so that my peaks align with my troughs and my troughs align with my peaks. So you can be 0 plus 0.5 lambda, you can be 1 plus 0.5 lambda, so on and so forth, okay? So it is important in our analysis here to know the thickness of the film, okay? We're going to call that thickness A, all right? So sadly, there are no equations for the thin film on your equation sheet, but the relationships between here that I'm going to discuss with you are very important to understand. So if you're given that, let's say, there's air on the outside, and let's say there's water, there's a thin film of water you're dealing with, let's then again understand where our displacement, our phase shift is coming from, okay? So notice that the first incident ray comes in contact with the boundary and then immediately reflects off, okay? So relative to the first incident ray, our second ray that's coming up right here is traveling through N2 and then traveling through N2 a second time to come back out. So it's traveling a distance of 2a as it comes back out. So now we can say that in order for there to be constructive interference, there must be a constant multiple times lambda equal to 2 times the thickness of our film, and the same condition for destructive interference. All right? Now, we can forget about the ray of light that goes into the third medium because we are assuming that that does not reflect back up, and if it does, it's reflecting sufficiently far away from the other two reflections. Again, this is a thin film for precisely that reason. So the final caveat to this thin film analysis is we need to realize that what we talked about before about the transmission / reflection still holds true here. Meaning if light is going from a place where the wave is traveling fast to a place that is traveling slow, that means the reflected wave will invert. If, on the contrary, the wave is traveling from somewhere where the speed is slow to somewhere where the speed is fast, the wave will not invert. It'll remain the same way it was, okay? So air going into water is an inversion because the speed of light in air is faster than the speed of light in water. So this wave will be 180 degrees out of phase, or it'll have a phase shift of pi, okay? Where pi, or 180 degrees, is a phase shift of lambda over 2, okay? Now, let's analyze what's going on in the second reflection, okay? If the speed of light in N2 is faster than the speed of light in N3, then this reflection will cause another inversion, okay? So if lambda is shifted here and lambda is shifted here by the same amount, then the net shift is 0, okay? If the net shift is 0, then we can forget about the phase shift caused when the reflection is inverted. However, if the phase shift occurs only at one of the two reflections, then we need to factor in the phase shift. Okay? So let's say that this N3 is N equals 1.1. So since this index of refraction is less than that of water, light will travel faster in N3. Therefore, we have a phase shift at the first reflection, but not a phase shift at the second reflection. So, in order for constructive interference, our displacement has become 2a plus the phase shift, which is lambda over 2. So now, to meet all our conditions, we need to add an extra term. So in order for constructive interference to happen, then some constant multiple times lambda must equal 2 times the width of our thin film plus lambda over 2. Okay, and of course we would need to be given lambda, or we would need to calculate it. If the problem specifically asked you for constructive interference and gave you lambda, you would plug into this equation and you would assume, like, let's say 1 for this. So this is going to be far and beyond the most encompassing and the most challenging part of this unit, so I suggest this is where you concentrate some of your practice. Again, I've got a Discord server, and enjoy life, guys.